Hello everybody, welcome to the Sun lecture. In this lecture we will study the Sun physical phenomena, how its heat is formed. We'll study the sunspots, the solar activity and the solar winds, and by the end of the lecture we will study the movement of the Sun in the sky dome using the altitude and azimuth coordinates. Okay, this is our outline. We will study, by the beginning of the lecture, we will study the solar atmosphere, the heat flow in the Sun, the photosphere, the chromosphere, the solar corona, and the helioseismology. Then we will study the solar activity and the sunspots and active regions, the sunspot cycle, the Sun's magnetic cycle, magnetic cycles on other stars, chromospheric and coronal activity, and the solar constant. Then we will study the nuclear fusion in the Sun, nuclear burning energy, hydrogen fusion, and the solar neutrino problem. And after that we will see the altitude and azimuth system and how our Sun moves in the sky. So this lecture is divided into two parts. The first part is astrophysics and the second part is spherical astronomy. So there are some general properties of our Sun, which is the Sun is an average star, its spectral type is G2, and we will discuss what is a G2 is, the spectral types. We will know what are spectral types and how can we identify them. It only appears so bright because it's so close to us. The absolute magnitude of the Sun equals 4.83, which is the magnitude of the Sun if it's at the distance of 10 parsecs or 32.6 light years. The Sun is 109 times 109 times Earth diameter, and it's 333,000 times the Earth mass. It consists entirely of gas with a density, average density, equals to 1.4 grams per centimeter cube. The central temperature of the Sun equals 15 million degrees Kelvin, and the surface temperature is 5,800 degrees Kelvin. Okay, please, very important warning. Please never look directly at the Sun through a telescope or binoculars, or even with your naked eyes, because we will see many phenomena, but never try to look at them on the Sun disk directly. There are methods to look at the Sun through telescopes, which is you hold the telescope and under the telescope you put a piece of paper, and using this way you can see the sunspots. But there are some phenomena that you will not be able to see using this method. You need to use H alpha filters and other filters to see the flares, for example, of the Sun. Okay, if you look at the Sun directly, this can cause permanent eye damage, even blindness. Use a projection technique or a special Sun viewing filter. So in the solar interior, the temperature is high. Then you move towards the photosphere. It starts to the temperature starts to go down. Then as you move up, the temperature increases. So it's very high in the core of the sun, but as you move up, the temperature starts to decrease, and then it starts to increase rapidly in the corona. And we will see one of the assumptions and the theories why this temperature increases so much and rapidly in the corona. Okay, first of all, we will study the photosphere, which is the apparent layer of the sun. Its depth is 500 kilometers and its temperature is 5800 kelvins, and it's highly opaque, formed by hydrogen ions. And it absorbs and re-emits radiation produced in the solar interior. Okay, this is the solar corona. It's around the sun, and we can see it clearly during solar eclipses. So, how does energy is transported in the sun, in the photosphere? Well, there are three main types of energy transport or heat flow. The first type is connectivity. It's when you connect two bodies to each other, when they touch each other, so that they start to transfer energy until they reach equilibrium. The next system is radiation, which is you give that body lots of energy, then it starts to the electrons start to excite and it emits photons and energy. And the last system is convection, and convection is the energy transport and flow through another medium. For example, in architecture, when you have a double glazing, so and there is a medium for convection, which is air in the middle. So here the temperature flow will be caused due to convection, and it's caused due to the flow from high pressures to low pressures, from low temperature to high temperature. And that's what happens in the photosphere. Cool gases sink down, and high temperature gases go up, causing bubbles of hot gas rising up, and this happens in an approximately 1,000 kilometers. And those bubbles last for 10 to 20 minutes. And this causes that we see granulation in the photosphere and the sun surface that is caused due to this convection. We see those spots that are cooler. The dark areas are the cooler, but they are not really dark. They are so bright, but they look dark because our naked eyes are sensitive to light, so it will make a comparison that will cause it to appear darker. So this causes the granulation of the sun surface, low temperature and high temperature, and flows inside and outside. Okay, the chromosphere. It's the region of a sun's atmosphere just above the photosphere, and it's visible, the chromosphere, and it's visible in the UV and X-rays lines from highly ionized gases. Temperature increases gradually from 4,500 kelvins to 10,000 kelvins, then jumps to 1 million kelvins. And the chromospheric structures are always visible in H-alpha emission filtergram. The H-alpha filters, they are filters that can make you see the chromosphere and the flares. Spicules, filament of cooler gas from the photosphere rising up into the chromosphere, visible in H-alpha emission, each one lasting about 5 to 15 minutes. The layers of the solar atmosphere. So this is the visible sun, it's just like that. But this is the ultraviolet, the sun captured in the ultraviolet. This is how it looks. This is the emission that we cannot see in the ultraviolet. So these are the sunspots. They are regions of very high activity. Very high activity are called the they show us the activity of the sun. Okay, the magnetic carpet of the corona. This is how the mechanism that seems the reason for the rapid increase of the temperature to 1 million degrees Kelvin. The corona contains very low density, very hot 1 million degrees gas. Coronal gas is heated through motions of magnetic fields anchored in the photosphere below the magnetic carpet. So the movement and the magnetic fields causes this high, very high temperature, and this is a computer model for the magnetic fields caused by in the corona.